Hey, we're working with related rate problems. And in this one here, we've got y is equal to x squared, dx over dt is equal to 2 feet per second. And when x is equal to 3 feet, and we're going to be trying to find dy over dt. Now, it's not really stated in this problem, but we can look at it this way. Pretend this is some little point right here, which he doesn't look very happy. But and he's moving along this curve. Okay, so you can think of yourself, let's say for example, walking, and you're walking along this path, which is described by this relationship here, y is equal to x squared. And you're walking along this path in the x direction when you're walking 2 feet per second. Now, this is the x direction, and I've got like a vector right here. Um, well, I've got an arrow, let's just say. And what's happening is you're moving in this direction at 2 feet per second. We're wanting to find what is your movement, your rate going in the y direction. Now, you might think of yourself as moving along the path, right? For example, if we looked at the tangent line to this path right here, okay, it would be like an arrow that's going off in this direction, and that's what you'd be more associated with, how fast you are actually traveling on the curve. But what we're looking for in these related rate problems is how fast you're going in this direction, the x direction, and then, for example, how fast you're going in the y direction right here. So that's kind of, this is what we're looking at when we ask for dx over dt, how fast you're traveling in this direction and how fast you're traveling in the y direction. Um, you can kind of think of it, for example, I don't know, pretend let's say you're standing here, right? And someone is walking along a path. And as you stand right here, for example, let's say that you're right here. As you stand right here and you watch the person, right? You're watching them as they move, okay? As they move along the path right here, you're going to measure, let's say, for example, you have someone standing here and someone standing, let's say, for example, right here. And as this, you hit the clock at 0, right? Start the stopwatch, and or actually somehow you're able to tell this person over here to start the stopwatch right when they pass you. And what you're measuring, and so you measure this distance, how long it takes this person to travel as they go along the path. But when they get to, let's say, right here, that would be, let's say, right here in front of this person here, right? This distance. Okay, so you'd hit the clock, and you'd be measuring. You know that it's a known distance, and you'd be measuring how long it took for this person to get from here to here, but we're only concerned about in the x direction, so that's what we're talking about. And then, of course, you could find the rate, right? Take the distance divided by time, it'd be an average. But anyway, that's what we're doing. All right, well, we better get started with this problem. So we took the derivative, and the derivative, remember, of x squared is just 2x. And what I've actually got going on here is I've got dy over dx is equal to 2x, and that's if you normally would take the derivative. And then what I've done is I've taken the dx over dt to both sides. I multiply both sides by dx over dt, and these guys cancel out, and you're left with dy over dt, and you end up with dx over dt on the right hand side. So anyway, I kind of thrown this in right here. Hope it doesn't confuse you on how do we actually come up with this tacking on this dy dt thing. But I don't know, that's kind of one explanation. Okay, so this is where we need to start. So we took the derivative, and it was 2x, and then we tacked on the dx over dt. And now we just plug in everything that they give us. So they gave us a 3 for x, dx over dt was 2. We multiplied it together, and it turned out that the point traveling along that path is moving at 12 feet per second, and that's in the y direction. Okay, that's in the vertical, like the vertical direction, the dy over dt.